Here is the 6.3.2 lecture focused on geometric random variables. And this particular video will focus on using the TI nspire for our calculations. We talked about in an earlier lecture the binomial setting, um, which involved binary, independent, set number of trials, and probability of success being the same on every trial. In this lecture, we'll talk about the geometric um, distribution, the geometric setting, which looks identical except for t. In binomial, it's an n for a set number of trials. In the geometric setting, we try until we get our first success. And if we count the number of trials till we get the first success, we'll have a geometric random variable. Um, it's important to make sure that we meet the criteria before we declare something to be a geometric random variable. The random variable will take on numbers from 1 to infinity, which is different than the earlier times. But let's jump into a problem. It says your teacher is planning to give you 10 problems for homework. As an alternative, you can agree to play the birthday game. Here's how it works. A student will be selected at random from your class and asked to guess the day of the week, for instance, Thursday, on which one of your teacher's friends was born. If the student guesses correctly, then the student will have only one homework problem. If the student guesses wrong, then your teacher will once again select a student from the class at random. The student will try to guess the day of the week for a different one of your teacher's friends on what day they were born. If this student gets it right, the students will have two classes, two homework problems. The game continues until a student guesses the correct day of one of your teacher's many friends. Your teacher will assign the number of homework problems that are equal to the total number of guesses made by the members of class. The random variable of interest in this game is called y, and it's the number of guesses until there was a correct match was made. Let's verify that y is a geometric random variable. First of all, is it binary? Does every trial end uh, um, in success or failure? Yeah, success would be guessing the day right, or failure, guessing the day wrong, and therefore, yes, it meets that criteria. Is every try independent? And the answer is yeah. Earlier successes or failures does not change the probability of future. So yes, it is independent. Do we try until first success? And that is, yep, that's exactly built into this particular guessing game. Okay, is it the same probability for every trial? And the answer is yes. And the probability of getting it right on any individual trial is 1/7. So, what's the probability that the student will get it correct on the first guess? Okay, well, let's say y is defined as a geometric random variable with 1/7 being the probability of success. The probability that y equals 1 is 1/7 because it was the probability of being right. What about in the second try? Probability of being right on being correct on the second try. Well, the only way to be right on the second try is that you had to miss on the first try, which has a 6/7 chance of success, and then you were right on the second try. And that looks like 6 out of 49, whatever that is. What about on the third? Well, you were wrong on the first try, wrong on the second try, but correct in the third try. So that would be like 6/7 squared times 1/7. Maybe I should have left this one like that. Okay. Can you see a can you see a pattern here? 6/7, 6/7, 6/7, 3 failures, 1 success, or it's 6/7 to the third power times 1/7. So the pattern is set, and what is that pattern? Probability that y is some value k is the probability of failure of k minus 1 followed by the probability of success to the first power. We have k minus 1 failures followed by 1 success. And that's what we have written down for our formula. Let's see if we can do this in a problem. It says let y be a random variable, y be defined in the previous example. Number of guesses to correctly match the birthday. Find the probability that the class receives 10 homework problems. Well, that's the probability that y is exactly 10, which will be the probability of how many failures? 9 failures followed by 1 success. And let's go ahead and let's pop that into calculator. I'm going to start with a new document. And so we could say that this is going to be shift division, 6/7 taken to the power of 9. And we're going to multiply that by, and I'll do control division, and I'll put my 1/7 there. And if I want a decimal version for the answer, I'll hit control enter, and it's about 3.5%, 3.6%. Now, I did that on the calculator, putting in this directly, but we can also find this value by going to menu, probability, distributions, and way at the bottom of the list is geometric PDF. Probability of success is 1/7, and we're looking for 10 to be our value. We got the first success on the 10th trial, and you can see we're getting the exact same number out. All right, probability of getting it correct in less than 10 trials. Well, there's 2 ways to handle this, but I'm only going to look at the one that uses the calculator. All right, and that is PDF is great for finding an exact outcome. How about a CDF for finding less than 10? Right? So if we go back to the calculator and we're going to look under menu, again, probability, try that again, probability, option 5, distributions, and again, way down at the bottom is the geometric CDF. We could say that 1/7 is our probability of success. Our lower bound is 1. We have to have at least 1 trial, and we want it to be done in less than 10. So less than 10 would be 9, from 1 to 9. And that's about 75% chance. So the probability of y being less than 10 is the geometric CDF 1/7, and our lower bound is 1 and our upper bound was 9. And again, we should document each of those numbers, lower bound and upper bound. And on here, we should have said this is probability and this is our outcome. Okay. All right. So we've handled how to find the PDF and the CDF. So exactly 10 is a PDF. Less than 10 is a CDF. But remember, we want to, less than 10 means the good outcomes are from 0 to 9. All right. Now, what about the shape of a shape of a geometric distribution? Well, the shape is always, always, always going to be skew right. And, although this feels contradictory, always the first outcome, the outcome that gets on the first try, that's always going to be your highest outcome. Always. Now, what about the center? Well, that's going to vary from trial to trial, but the center is the expected value. And we're going to see down below that the expected value is 1 minus p. So the expected value um, for this particular thing is going to be 1 over 1/7, which is going to be equal to 7. Now remember, this 7 is here, but remember this tail goes out infinitely. And then our formula for spread is there, and it's square root 1 minus p over p. So square root, so there should be a y. The square root of 1 minus p over p, which in this case is the square root of 1 minus 1/7 divided by 1/7. Okay, and we can put that into our calculator and find that out. Again, square root, and then I'm going to control division, 1 minus, and then I'm going to do control division to get the 1/7 in, 1/7, and this is all going to be divided by 1 divided by 7. Control enter, and there's our standard deviations, 2.449. 2.449. There we go. All right, let's do a little check for understanding. It says, suppose you roll a fair pair of six-sided dice until you get doubles. Let T be the number of rolls it takes. Is this binary? And the answer is yes, because every trial ends in either success, you got doubles, or failure, you didn't get doubles. So that's true. Is every trial independent? Well, it is if we're using fair dice. Are we trying till first success? We certainly are, because we're trying until we get our first pair of doubles. Is there the same probability on every trial? And yes, there is. And that probability is 6 out of 36, or 1/6. That's the probability of getting doubles. So what's the probability of getting doubles on the first pair of doubles on the third try? Well, that's the probability. Again, that T is 3, and that's 5, 6. That's a failure on the first try. 5, 6 again, failure on the second try. And then 1/6, we get our success. 5, or 5, 6 squared times 1/6. That's going to be 25 over 316. No, that's not right. What is 36 times 6? 6, carry the 3. 216. All right. And again, on the calculator, we could say 5, 6 squared, and then multiply that by 1/6. Control enter, about 15 or 11.6%. 0.1157. All right. In the game of Monopoly, you can get out of jail by rolling doubles within 3 turns. Find the probability that this happens. This problem is not geometric because you either get your doubles, which happens 1/6 of the time, and you're done, or you don't get doubles, 5/6. You get doubles on your second try, or you don't get doubles, 5/6. You get doubles on your third try, or you don't get doubles. Okay. So, well, I suppose we could think of it this way. Um, Within three terms, so this is either the probability of getting out on exactly one, or the probability of getting up on the second try, or getting out on the third try, which sounds to me like a geometric CDF, um, and our lower bound um, probability of success is 1/6. 1 through 3 is our choices there. So let me see if I can pull that out. Menu, probability, distributions, geometric CDF. 1/6 is our probability of success. And we want probability of getting out between 1 and 3 times. Getting the doubles between 1 and 3 times, which happens about 42% of the time. All right. And that concludes our very, very short discussion about geometric random variables.